Today we'll start with some motivating applications, okay, where parallel computing is heavily used, right. So let's start with one such application, which is finite element method, right. So last time we spoke about things like when you manufacture cars, right, you need to do things like car testing, right, car crash testing, where you want to figure out whether the car can sustain certain accidents or not, right. So what does that involve? That involves the action of a lot of forces on the car, right, and you want to analyze what is the deformation that happens in the car when you try to do something like that, right, when it crashes. So how do you generally end up modeling the car? So you have the car, and typically what you do is you end up dividing this into a mesh, okay, some kind of a mesh. So there are different structures, so we won't get into details of that. This is not a course on finite element methods, right, but essentially the crux is that you divide it into a lot of elements, okay. So there are something called nodes, right. So all these points over here, they basically refer to the nodes, right. So that's the structure of the car. And then there is something called the elements. So the elements can have different dimensions. So it can be the links which are connecting these nodes, and so on. There are more complex elements as well. The crux is that I want to understand that what is going to be the deformation in this car if, let's say, that there is some big rock that falls on it, okay. So what happens to this car? So obviously, as you can expect, there will be some kind of deformation. Maybe the ceiling of the car will cave in, right. So you want to actually figure out exactly how much that deformation is going to be. So how do you do that? So you can do it via computer simulation, and what you do is you divide this entire car up into a very fine mesh. This mesh is like, it has lots of nodes and elements, right. Earlier, scientists used to, because of the limitations in the compute power, they used to divide it up into, say, about thousands of nodes and elements. So obviously, if you divided it up into thousands of nodes and elements, the results are not that accurate, right. The finer your mesh, the more accurate your results are going to be. So then people got more and more ambitious, and as the computing power started increasing, they started to increase the size of the mesh, right. So nowadays, I mean, it's very common to find millions and millions of nodes in a mesh, right. So you want to really know accurately what was going to happen to the car. Another very common scenario where this is used heavily is in analysis of what happens to a mobile phone when you drop it on the ground, right. That's a very, very common incidence, right. So I mean, this is very normal testing that mobile phone companies do, right. So again, that is also done by the same thing. We want to figure out what is the deformation if some forces are acting on the car. What happens is that you have lots of variables. So for each node over here, right, you're going to have some variables which may be corresponding to the location, the acceleration, velocity. So there will be a lot of variables that will be associated with this, with each node, right. And then these elements between the nodes, they are kind of going to represent some of these stress and strain relationships that are interacting between the nodes. So there will be an equation, either a stress or strain equations, which will basically tell you what is the relation between the forces acting on these two nodes. So for instance, if a certain force acts on one of these nodes, what is going to be the effect on the other node, right. So there will be some stress and strain equations. Again, we are not going to go into the details of that, but the crux is that, so there is some variables related to this node I, some variables related to node j, and then there are some equations which are going to relate these two, right. So you will have some equation over here which is going to have maybe a 1 over here, a 1 over here, right. It's relating yi and yj, sorry, this is j, right. So it's relating yi and yj, and it's representing some of the stress and strain equations. Now let me write it down in matrix form. Let's say this column represents yi, right. What does that mean? That means that if I multiply this matrix, so this matrix is a matrix of numbers, right, floating point numbers. So what I'm going to multiply this by is, there's going to be an xi variable here, a yi variable here, xj variable here, yj here, right. This corresponds to the respective columns, right. So when you multiply each of these rows with these variables, the product is going to be the entry over here, right, and that's going to be one equation, right. So eventually what do you have? You have a system of equations, right? Ax equal to b, and you want to find the solution to this, right? And now when you're doing this analysis, so it's basically an iterative step where you keep on applying the force externally, right? So when you apply the external force on this, maybe you set on the right hand side, you set some values depending on the force, right, to some particular values, and then you want to solve the system of equations and figure out that what is the solution. A lot of these methods, even those which are not directly solving system of linear equations, they are non-linear problems, even they are reduced to linear problems either by Newton method or other methods, and eventually it turns out that Ax equal to b, solving this turns out to be a very important problem. And as a matter of fact, if you look at the top supercomputers of the world, right, the top 500 listing of the fastest supercomputers in the world, they are benchmarked on solving a system of linear equations. So this is a very important problem in scientific computing, solving a system of linear equations. So let's get a little bit deeper into it. So you've done this before. How do you solve a system of linear equations? Let's understand that. And then we are going to talk about how are you going to parallelize it. Of course, supercomputers are built out of multiple nodes. So you have to communicate, you have to divide the problem up. So we're going to talk about all that, right? So we'll start with solving a system of linear equations. Okay, so how do you solve a system of linear equations? So we've all done this at some time or the other, right? The simplest way to do it is Gaussian elimination, right? That's one standard way of doing it. Let's take a simple example. So let's say that there are three equations and three variables, okay? So everybody understands what this is, right? This is x1 plus 2x2 plus 3x3 equal to 14, 3x1 plus x2 plus 4x3 equal to 17, and 5x1 plus 3x2 plus x3 equal to 14, right? Yeah, so how do you typically do this? So typically you have lots of right hand sides to solve. So what you do is that you basically first, without looking at the right hand side, so this is your A matrix, you decompose A into LU, okay, where L is a lower triangular matrix and U is an upper triangular matrix. So what am I solving? I am solving Ax equal to b, and now I have basically reduced this A to LU, right? So it's become LUX equal to b. So how do I solve this? Well, let me for the time being assume this to be some variables x prime, right? So I have my lower triangular matrix, I have a set of variables x prime, and I have the right hand side. So I can solve this. This is simple. If you are given a lower triangular or an upper triangular matrix, it's straightforward to solve this, right? Why? Because this is your lower triangular matrix, this is your x1, x2, x3, and this is your b1, b2, b3, right? Right hand side. So what does that mean? That means that if this is a1, that you can straight away read off the value of x1. x1 is b1 by a1, right? And then you substitute x1 in all the remaining equations, and then you can solve for x2, right? And then you substitute that in all the equations, you can solve for x3, right? So this is called back substitution. So instead of solving Ax equal to b, you first decompose A into Lu, a lower triangular multiplied by an upper triangular matrix, right? Then you first solve Lx prime equal to b. Now you have your L, right, the lower triangular matrix, and you have your right hand side, you solve that. Well, this is going to give you the value of x prime. So now you have your set of variables x prime. Well, what is x prime? You had substituted x prime for ux, right? So you have your upper triangular matrix now, and you've already got the solution for x prime. So you can again do another round of back substitution and you're done, and you get the solution. All right, so let's start with the example that we set out with. And the way you do the LU decomposition using Gaussian elimination, right? So what can you do? You first say R2 goes to R2 minus 3R1, right? And how do you do this, right? So this is an elementary operation. How do you perform this elementary operation? So what we are going to do is we are going to keep an identity matrix, right, and this multiplied by this matrix. So this is your A matrix. Right. So identity times A is A, right. So what we are slowly going to do is we are going to convert this into L and we are going to convert this into U, right, upper triangular, lower triangular and upper triangular respectively. Alright, so how do we perform this operation on this matrix? So we want to convert this to upper triangular, right. How do we perform this operation on this matrix? So the way we do it is we pre-multiply it, if we pre-multiply a matrix by so R2 goes to R2 minus 3R1 is captured as follows. So R2 minus 3R1, right. This is the matrix that represents the elementary operation R2 goes to R2 minus 3R1. Okay. So all we do is we want to pre-multiply this particular matrix with this matrix. So I'm going to do this 1 0 0 minus 3 1 0 0 0 1 pre-multiply 1 2 3 3 1 4 5 3 1, right. And if you look at this, when you perform this operation, it's nothing but R2 goes to R2 minus 3R1, right. What I want to capture is I want to modify these matrices so that the product of these two matrices continues to remain to be A. Yeah. So how can I do that? Well, I basically take the inverse of this operation, of this elementary operation, right. I pre-multiply the product of these two matrices with the inverse of this matrix, right. So what is the inverse of this matrix? Well, for these elementary matrices it's quite simple. It's just the identity matrix with the sign corresponding to the other rows and columns changing to negative, right. That's basically how you pre-multiply. Okay, and I have my identity matrix to begin with, right. So now if I look at this product, right, and separately I look at this product, okay, this is basically going to take one step towards becoming upper triangular, okay, and this is one step towards becoming lower triangular. So when we perform this operation, what do we get? What does this become? This becomes 1 2 3 3 minus 3 0, that was the whole purpose. 1 minus 6, that is minus 5, and 4 minus 9 minus 5, right, and this remains the same, right. And what happens to this matrix? Well, this is identity times a matrix, so that's going to be the matrix itself. So this matrix becomes, right. Is it clear? So what have we done? Let's just look at this again, right. What are we really doing? So what we are doing is we had this A matrix and we had this identity matrix, right. I performed some elementary operation E on A, right. So if I just multiply by the inverse of E, right, and this is identity, right. So let me call this E1, right, then I'm going to get back A. This entire product is going to be A. So this is going to be some matrix, right. I'm doing Gaussian elimination. Now what am I going to do? I'm going to do another elementary operation on this, an E2 operation, right, E2 E1A. And so where does E2 inverse come? Well, it comes at the end. E2 inverse, E1 inverse, identity. This is going to be my new right side matrix. This is going to be my new left side matrix, right. Okay, let me write this as U. Eventually, it's not upper triangular right now, but it's slowly becoming upper triangular, right. So I'm doing elementary operations on the matrix A in order to make it upper triangular, right, and I correspondingly keep multiplying by the inverses in the reverse order on the right hand side of identity, right, and eventually what I'm going to get is a lower triangular matrix. Okay, and you can see easily, right, that E2 inverse times E2 is going to be identity, E1, and then what you're left with is E1 inverse times E1, which is again identity. So eventually you're going to be left with matrix A, right. So let's quickly see that in this example. So this is what we have. So what is the next operation I want to perform? Well, the next operation is R3 goes to R3 minus 5R1, right. That will make this element 0. Eventually my goal is to make it upper triangular, right, using Gaussian elimination. So what am I going to pre-multiply by? So it's just the identity matrix with the modification that R3 goes to, so the third row goes to R3 minus 5R1. Yeah? Okay. So I'm going to multiply this by this matrix, and at the same time I'm going to take the inverse of this, which is nothing but 1 0 0 0 1 0 5 0 1, and post multiply 1 0 0 3 1 0 with this, right? And what do I get as a result of this? Let's just quickly see what happens to this product. Well, it's same as R3 goes to R3 minus 5R1, so this will be 1 2 3 0 minus 5 minus 5, this will go to 5 minus 5, this will become 0, 3 minus 10 minus 7, and 1 minus 15 minus 14, right? Okay, and what happens over here? Let's check this out. If you look at a row over here, right, this is nothing but saying that take 3 times the first row plus 1 times the second row plus 0 times the third row, right? So it's easy to view it that way. So what happens over here? This is just going to be 1 0 0, and then this is going to be 3 3 1 0. Can you see that? Yeah, and the last one is just the last row 5 0 1. Okay. So the matrix on the right is becoming upper triangular and the matrix on the left is becoming lower triangular, right? So let's do the last step for the sake of completion. What do I have to multiply this by now? 1 2 3 0 minus 5 minus 5 0 minus 7 minus 14, right? And I pre-multiply this by, so what is the operation I want to perform? R3 goes to R3 minus 7 by 5 R2, right? That will make this entry 0. So, and finally I'll have an upper triangular matrix. So how do I capture that? 1 0 0 0 1 0, R3 goes to R3 minus 7 by 5 R2. Okay, and let me multiply by the inverse of that, right? And what is my L matrix? Currently it's of the form 1 0 0 3 1 0 5 0 1. This will be 1 2 3 0 minus 5 minus 5, and the last one will become 0 0, and so this will become, the last entry will become minus 14 minus 7 by 5 times R2. What is R2? Minus 5, right? So 5 5 cancel, this will become plus minus 14 plus 7, which is minus 7. Okay. And what about the left hand side? What happens when you multiply these two matrices? What do you get? Well, again, this is just the first one, 1 0 0 3 1. Oh, hold on. Why do we have 1 1 over here? This is a mistake. This should have been 0, right? This is just the inverse of this, right? Okay. So this was 0 1 0. So then what is this? 3 1 0 times this will be 3 1 0, right? Yeah. Okay. And what happens to the last one? This is 5 times the first row plus 1 times the last row. So what is that? That is 5. 7 by 5, 1. Okay. And that's it. You have your lower triangular matrix and your upper triangular matrix, right? That's the LU decomposition. Here we are doing Gaussian elimination, converting A to U, but simultaneously we are keeping track of the L matrix as well, the left matrix. That's all LU decomposition. It's just a slight modification of Gaussian elimination where you are also keeping track of the operations being performed on the L matrix. So what is the cost of Gaussian elimination? Where does the cost of Gaussian elimination come from? So if we are trying to solve a system of linear equations, what all steps do we have to do? We have to do an LU decomposition. After that, remember we talked about back substitution. We have to do back substitution. So what is the order of these operations? What is the complexity of these operations? So first of all, let's go to Gaussian elimination, right? What happens in each iteration of Gaussian elimination? I pick the pivot, right? Using this pivot, what do I update? This entire part of the matrix is updated, right? So what is the total number of operations I am performing in one iteration? It's order n square. Well, n is reducing it at every iteration, some alpha n square plus alpha n minus 1 square and so on, right. So what is the complexity of this if you sum this up? This is order n cube, okay. Because we are doing this for all iterations, right, we go diagonally down, right. So the total complexity of doing this is order n cube, Gaussian elimination, right. And what about back substitution? So what is back substitution, right? Let's quickly recall. So once I decompose into LU, right, then I do LUX equal to B. So first I already have my L, I have my right hand side. The thing I have my U, what I don't have is X. I want to solve for X, right? That's solving a system of linear equations after doing an LU decomposition of A. So assume that Ux is X prime, so then I have to do Lx prime equal to B. First I solve this. So L is lower triangular, X prime is the set of unknowns. Well, it's not the final unknowns I want, but this is just a set of unknowns I'm dealing with temporarily, right? And B is the right hand side. I already know L and B, right? How do I solve for X prime? This is lower triangular, right? So this times x1, x2 and so on is equal to the right hand side, right? So the first equation is just involves one variable, right? A single coefficient multiplied by x1, everything else is 0. So it's just an equation in x1, that's it. So I just straight away get the value of x1. Now I substitute that value of x1 in all these elements. Using the next equation I solve for x2 because x1 is not there anymore. I've already solved for x1, I've already substituted the value for x1. So in the second equation was originally in x1 and x2, but x1 you've already substituted the value. So you just have x2 as a variable, so you solve for x2. This is back substitution. And once you do this, so this gives you x prime. You get the solution x prime. And now what was x prime? X prime was nothing but what I had considered u times x to be. So you take ux equal to x prime and again do back substitution. U is upper triangular now. Back substitution works just the other way around. And you solve for x. What is the complexity of back substitution? So what is the crux of the operation? Where is the crux coming from? We don't really care too much about back substitution, right? Because that's not the bottleneck. I mean, the computation lies in doing the Gaussian elimination. Therefore, I concentrate on how to parallelize Gaussian elimination, okay? So suppose now that you have P processors. If you have like 100 millions of nodes and elements, so your matrix is huge, right? It will take you very, very long if you want to solve the system of linear equations on a single node. So now let's say that you want to do this in parallel. So if you have P processors, how are you going to do this in parallel? How am I going to do Gaussian elimination or the LU decomposition in parallel? So one way of typically doing parallel programming is that for every element, right, of whatever data you're dealing with, every element you give it to some processor. Right, so that's you're distributing the data and that processor has ownership of that element to update that element, to figure out what the new value is, right, to always maintain that element, okay. The ownership can change during the parallel programming, but I mean this is one of the standard techniques of solving a parallel program. So what do we do over here? We can divide up this A matrix, right. So we had this huge A matrix, we can divide it up amongst the P processors. We'll talk about how we can do Gaussian elimination then. What is the simplest thing that comes to your mind? Just divide the rows amongst P processors, right? That's a very, very simple way of doing it. So I'm going to give this to node 0, I'm going to give this to node 1 and so on, and the last set of rows is going to go to node P minus 1. So I'll number my node 0 to P minus 1. And each one of them, let's say that I have an n cross n matrix, right? Let me just assume that, then each one of them gets n by p rows, okay. So this is called the row block distribution. So I can do the same thing when I'm doing LU decomposition. I can assume that the same distribution holds for L and U also, right, that L is also divided amongst the same processes in the same way, U is also divided amongst the same processes in the same way, okay. Let's go back to simple Gaussian elimination, right? What is the first thing I need to do in the first step? I identify this diagonal element as the pivot, right? let's say that currently I am on the I comma ith element, right? I am always looking at diagonal elements. So currently let's say I am on the I comma ith element. So what's going to happen? What do I have to do? Every row has to update rj goes to rj minus, right, whatever is the element under that diagonal element, which is what? Which is the aj ith element, right? Jth row, ith column, right? aji by aii into ri. Is that clear? So what do I need for this? This ith row, where is that residing? That's residing on some processor P, let's say P naught, right? And let's say we are talking about Rj, which is residing, well, I have to update each and every row. So this means let me pick up one which is residing on P1, right? I'm updating a row which is on P1. So what does P1 need from P naught? The entire row, pretty much the entire row, right? From the diagonal up to the end. Is that clear? So the entire ith row starting from the diagonal element has to be sent to which processor? P1, and every processor has some row or the other to compute, to update, right? You have to update all the rows. You have to make all these entries 0, the entries under the diagonal, right? So what's going to happen over here? The owner of Ri will broadcast Ri or whatever diagonal till the end to all the processors. This is called a broadcast operation when you are sending the data to all the other processors. Okay, so once everybody gets Ri, now it's simple for them. They have AII also. Everything else is local to them, right? They have Ri, they have AII, which is part of Ri anyways, right? And everything else is local, right? So everybody can do the update. So this part is clear? Okay, now we get into something interesting. Is this a good distribution? Distribution is very, very critical. Let's understand why. Is this a good distribution? So I starts from 0, 1, 2 and so on. Once it reaches n by p, once n by p rows have been taken care of, what's going to happen? So this is the first processor P naught, right? So let's say that you've already done all this. All of this, you've already zeroed all this out, right? Now you're over here. So what is the parallel part over here? What is happening in parallel? All the RJ updates are happening in parallel. Going down diagonally one by one, down the diagonal is happening sequentially. But when you pick up a pivot and you say that I want to update all the rows, RJs, with this, right? All these operations, these are happening on all the rows. These are all happening in parallel. That's the crux of the operation, right? At a time, you are going to look at one diagonal element. This is not happening in parallel. You're not picking multiple diagonal elements in parallel. You're picking up one diagonal element, the pivot. For that particular row, you're broadcasting it to all the processors, and then all the processors in parallel are going to update their own rows, right? Okay, that's the parallel part, and that's the bulk of the computation, right? There is something wrong with this distribution, right? And that's what I want to highlight, and hence the whole point is that you have to be careful when you do parallel programming. You have to be careful about how you distribute your data. So here's the problem. When you're done with the first n by p rows, when this is the pivot, what are you going to do? You're going to broadcast this to all the processors, sure, but the point is that P naught has already done its work. That work is already done. P naught has nothing else to do for the remaining computation. You're wasting one processor for the entire computation. I mean, n by p rows is nothing. The remaining n minus n by p rows, P0 is doing nothing. It's a wasted processor. Is this point clear? Because it has nothing to update. You only update the entries below. Okay? So after another n by p, when you reach 2 n by p, 2 processors are going to become idle. And so on, right? So this is really not efficient. This is quite a bad distribution. Okay? So how do you fix this? Well, do you want to try columns? Distribute the column instead of the rows? Well, that's also not going to work, right? Because after n by p, again the first n by p columns will be all zeros, it's already reduced. You have nothing else to do. So again, the processes will be idle. So how do you do this? Here's a neat trick. So that's called the block cyclic distribution. So let's say you have P0, P1, P2, P3, right? 4 processors. Give R0 to P0, first row to P1, second row to P2, third row to P3, and then fourth row again to P0, fifth row to P1, sixth row, seventh row, and so on. So this is called, sorry, this is not called the block cyclic distribution, this is called the cyclic distribution. You just cycle the rows amongst the processors, right? And now can you see that you will not be wasting computation? Yeah? Every processor will be busy, right? Till about the end, right? And in the end, I mean, there will be some p rows that will be left when you will have uneven distribution, which is fine, I mean, that's okay. And it turns out that, cyclic distributions are not that great, we'll study that because they are not cache efficient. There is actually something called the block cyclic, which actually turns out to be better. You basically take the matrix, give a block of B to P0, give the next block of B to P1, give the next block of B to P2, next block of B to P3, then next block of B to P0, and so on, right? And this is purely for the reasons of cache efficiency.
Block will be cache line size.
How do you do Gaussian elimination? What is the basic underlying operation in Gaussian elimination? Matrix multiply. You do Gaussian elimination by doing matrix multiplies. Okay, and for matrix multiplies, you've got to ensure that the matrices you're multiplying and where you're storing the results, all of them fit in the cache, in the L1 cache, right? That's where the block size comes in. So anyways, let's not worry too much about these things right now. We'll get into them slowly, okay?